العافية جميعا. خلال السنة الماضية خلال الفصل الماضي عملوا ميرا دانيا بمشروع تخرجهم تحت إشراكي. اليوم حابين يعرضوا عليكم نتائجهم. طبعا عنوان المشروع Tested up for Transdigital Processes. طبعا بوزع عليكم، تفضل.
Good morning, everyone. First of all, we'd like to thank you for attending our project's defense. We'd like to introduce ourselves. First of all, I'm Dania Abdelqader Graduation. And as Dr. Nassim mentioned, we've been working for the past year on designing and building a unique test setup for transtibial prosthesis, which are also known as below-the-knee prosthesis. We will guide you through the whole process of building the setup, starting from explaining the motivation, scope, and objectives of the project. Next, we will explain some theoretical concepts that are important for understanding the operation of our system. And finally, we will discuss the design and implementation. First of all, the first step of building the setup was to consider the importance of such a setup in the market. So the first thing that came to mind was the fact that lower limb amputations are the most common types of amputations in the world. And in Jordan, the most common type of lower limb amputation is the transtibial one. Therefore, this highlighted the importance of optimizing the design of transtibial prosthetics, which would benefit the user, in which it would produce higher quality products with with better fits, and it will also benefit the manufacturer in that it would reduce patient testing costs and would save time. Okay, now we will discuss the scope and objectives of our system. The scope and objectives was to design a system that is able to imitate normal human walking by having the same angles and loadings as any gait cycle. Second of all is to simulate various walking environments by giving the option of testing prosthetics on both flat and inclined surfaces. And this is very important when testing prosthetics that are to be used in Jordan, because as we all know, Jordan has a lot of hills and inclination. Third of all is for the system to study kinetic, kinematic, and dynamic aspects, and based on international standards. The baseline for our design was the ISO 22765 and the ISO 10328. In addition, the system had we wanted the system to give us quantities and values that reflect on the performance and durability of the product. To start with some theoretical concepts that will allow us to understand the setup more. The first thing we did is that we tried to see the earlier test setups that were designed and developed by other people. So the first, we took some of the setups that we found to be most interesting. The first one, which is shown in figure 1, is a dynamic loading machine. It was produced by Weavers and Durance in 1987. And basically, we have a cam driver mechanism at the bottom that allows the leg to move and mimic normal gait. The second one, which is shown in figure 2, is the NPO fatigue tester. It was developed by Ziolo in 2001. It uses, however, air compressors that drive pneumatic cylinders that inflict loadings on the prosthetic. And the third one is the MTS machine, which has been used by Berglund in 2010 in order to test the prosthetics. It utilizes a 4-bar mechanism in order to mimic gait. A very important concept to understand is the gait cycle, because our design is really focused on achieving movement similar to the gait cycle. The gait cycle consists of 2 phases. First of all, we have the stance phase shown in green. It is divided into various parts: the initial contact, loading response, mid-stance, terminal stance, and pre-swing. and it takes up 62% of the total gait. Then we have the swing phase, which consists of initial swing, mid-swing, and terminal swing, and makes up 38% of the total gait. What was important here is what's important in general is that every phase consists of a correspondence of the hip angles, knee angles, and ankle angles, and this was an important part of prosthetic, that is a device fitted to basically substitute for a lost limb. So there, due to the high focus of lower limb prosthesis, especially in the medical sciences, has led to the various types of lower limb prostheses, which are fitted in accordance to a person's height, age, level of activity, but most importantly, they're divided or categorized according to the level of amputation. So it only makes sense that the higher the level of amputation, the more components are required. So if we were to divide them in accordance to those categories, we have the foot or partial foot prosthesis, which is basically only a foot and an ankle. And then we have the below the knee, which is a prosthetic that is below the knee component. It does not involve the knee component, as opposed to the through the knee prosthetic, which involves the knee component that can bend and extend and can generate movement required for walking and sitting and running. And then we have the above the knee transfemoral prosthetic, which is basically a prosthetic, as its name suggests, that's above the knee. So, and along with the knee component, it also has a pylon or a shank, which you can see here between the knee component and between what is considered the hip socket. And then the most severe or the most extended type of lower limb prosthetic is the hip disc articulation, which basically involves all the components you can see in this figure. So we can see, like I said, the foot, so the pylon, which attaches the foot to the knee joint. We have another pylon between the knee joint and the hip joint, and we have the socket of the hip. So in addition to the different types of lower limb prostheses, we also have different types of feet. So we can see the first type here in the figure is a single axis foot. And as its name suggests, it only moves in one axis. So it only performs or generates up and down movement. So it only goes about the y-axis. In contrast to the multi-axis foot, which moves in three different axes. So it not only moves up and down, but it also moves left and right. And we have the third foot, which is a dynamic feet. And this type of foot is basically considered the most responsive kind of foot. So it's intended for users that require a very active foot, that not only works efficiently in the means by which it moves, but it has a good energy return. So as you're walking using the dynamic foot, it absorbs energy that is generated through the gait cycle, as a human leg does, as a human foot does, and it returns some of that energy, so it's energy efficient. And the last foot here we have is a sack foot, and the sack is a well-known commercial foot, and it's known for its good price. It's very economical, and it has a heel cushion, which basically allows for a comfortable heel strike. In addition to the heel, which provides a stable mid stance. And now we're going to talk about the design of the setup and the different sectors that we actually executed in a thorough manner. We have first the structural design, and we're going to discuss what went into the decision of the dimensions that we used for the structure. And then the mechanical system design and the early models that we implemented, the decisions that we had to take to choose the mechanism that's well suited for our project. And then we're going to explain the data acquisition system, which as any acquisition system involves a sensing unit to acquire the physical environment, and an actual selection which receives the command from the data acquisition or the microcontroller itself, and generates a sort of function. And then so here we have the two main concept designs that we came up with for the structure. We have the first one is a movable ground design, and in this design we have, as you can see, there's less components than the design shown in figure 8. And in this design we have the knee component. We have the distinctive feature here is a movable platform. So this is considered the platform or the ground, and it's driven by and it has pistons that are driven by a motor and a gearbox. So what that does, it allows a vertical movement up and down, and that basically mimics the gait. So as the foot moves, the foot doesn't
need to be movable because the ground is basically subjecting the movement on the foot itself. In contrast to here, where we can see we have a lot more components, we have a 4-bar mechanism. I'll explain what a 4-bar mechanism is in the next slide, but for now the 4-bar mechanism represents the hip. So we have an additional hip. We have the knee, which is driven by another motor. So we have two motors, which costs energy, but in return, this system is more flexible, and we're able to study more kinetic and kinematic aspects of the prosthesis itself. Also, we have a spring on the bottom of the platform, and what the spring does is it basically performs like a loading and a release on the foot. In addition to the structural designs itself, we have we came up with a ground that is movable, but in a means where it will save energy, and it has two distinctive features. And by that I mean, number one is the platform itself is driven solely by the impact of the foot, meaning it will slide backwards when the foot subjects onto the platform. So no motor is required for its movement. In addition, it also has inclination variant feature, where we can simply just shorten the chain, the industrial chain on one side, which causes some form of inclination, and that's really good when we want to correlate to the testing of prosthesis in grounds that are considered uneven and grounds that have some form of inclination, especially in Jordan. We know that Jordan's grounds are not very smooth, and the terrain is pretty hilly, as Mira mentioned earlier. Before we get into the mechanics of the system, we needed a reference, and by reference I mean we needed the movement or the projectile of a normal human foot. And to do that, what we did is we obtained the data sheet of a knee trial that our professor provided us with, and we basically plotted a graph of the cycle phase against the knee position. And the blue, as you can see, is the movement of the left foot, and the orange is the movement of the right foot. So the movement of the right foot in orange is what we use for the projectile or our reference, so that when we tried to obtain the mechanism we wanted, we looked at this trajectory and we tried to obtain a very similar one. So before we did that, so a 4-bar mechanism in general is a mechanism that propelling a body forward. So the 4 bars are called the crank, the coupler, the rocker, and the frame. So what we did is, the obstacle that we faced with the 4-bar mechanism was trying to figure what dimensions are required for the 4 bars in order for them to work on propelling the body in a manner that will give us a trajectory similar to what we obtained in the previous slide. So what we did is we used an online simulator, and in this online simulator we started inputting values for the 4 bars. It's not very clear here, but we inputted the values in these 4 bars, and through trial and error, we kept on working on the generated projectile until we obtained one that very much resembles what we wanted, and we were very successful in that. So to further justify whether our dimensions were going to give us a correct projectile, what we did is we built an early prototype somewhat. And here you can see we brought carton paper and we cut them in the dimensions that we obtained previously in the animated simulator, and then we attached the little pencil onto the coupler, and we drew the trajectory that we obtained through using these dimensions. And we were very successful in obtaining a desired projectile. So even though we were successful at building an early model for the 4-bar mechanism, we then decided to investigate the 6-bar mechanism, because the 6-bar, although it's complex and involves more number of bars, more components, it does generate a movement that very much resembles that of the human. So the 6-bar mechanism has already been used successfully in knee prosthetics, and we can see here, we can see the way the 6 bars move together in order to propel the body forward. It's kind of hard to visualize it through pictures, but we'll show you a video later on so you guys can see how the bars move and correspond to one another. So what we did is we then needed to build another prototype for the 6-bar. So to obtain we also had another obstacle trying to obtain the dimensions again for the 6-bar. So what we did is we took the 4-bar dimensions